Hi everyone, my name is Xihao Zhou, the project manager for Team3. Today I'm going to be your presenter. Our team works on a project called Tool Finder, which is a scientific software classification project. Let's go into the details.
First, let me introduce my teammates to you guys. My name is Xihao Zhou. I am the project manager. We do have three other machine learning experts, Rohan Gao, Hao Yang, and Yifan Li. One software engineer works for us, is Gan Xin. He will take the responsibility to build the reproductive environment. And Dongshen Yang will collect data for us. He is a data management expert. Then it's a problem we are trying to solve. Recently, a lot of software developers and scientific researchers, they often face the same issue, which is it takes a too long time to search and find the suitable softwares that best match their needs. And the descriptions of these softwares are usually actually too long to read. Also, they often faced a lot of bugs, a lot of troubles during the building process of their working environment. So we want to find something, we want to come up with a project that can help them solve this problem, can actually save their time. Before we get to start, we actually searched for previous works, and we do find one very helpful project called SOMEF. We can see the website for this project from here. The aim of this project is to help automatically extract metadata from scientific software from their README files that can be found on GitHub repository. By doing so, we can actually know which sentence in that file belongs to what kind of metadata, like if sentence A belongs to description, if sentence B belongs to installation. Okay, based on that project, SOMEF, we set the following three different objectives to follow. The first thing we want to do is to improve the performance of SOMEF. It's kind of a classifier update. We want to improve the prediction rate by increasing the F measure, and we're hoping to have a better result than all the existing ones that has been recorded in SOMEF. Next thing we want to do is to build a new classifier for functions. For doing that, we want to be able to take the input as a URL link or some articles, text input, and then return our prediction of these functions of those softwares. Like if you give me a URL link, I can tell you, oh, this URL represents what software it does what. And the last, we want to visualize our result because the purpose of our job is to save our users time on searching those software. So I want to make them comfort on looking at the results. So an interactive interface for them to use will be better to understand and read our results and can actually save their time from reading tons of words. Okay, now let's take a brief look at our workflow. This is kind of a simplified version of the workflow. It's not that detailed, but actually you can get a basically sense of what we are doing, what we have done. At very first, we just download the SOMEF and we extract it and we take the record of the existing models. And for the citation, installation, and invocation dataset, we actually do nothing to them, just use the same dataset and train our new models with some new algorithm to try to improve the performance. But for the description dataset, we actually choose to expand the size of it to enlarge the corpus to have more data. So use that new description dataset, we trained two classifiers. The first one is the function classifier. Another one is the description classifier, which is a binary classifier for description. After doing all these jobs, we trained all the classifiers, we saved all the best models, we will create an interactive interface for our user to see our result, to interact with us. The binary classifiers for the metadata. It represents the following part in that picture in the workflow. And at very first, we want to handle the input. Because the original input we have are sentence, our text. And the first thing is to get a sense of the size of the input dataset. By collecting the dataset from the repository of SOMEF, we count the numbers of the samples, and we notice that description has 336, installation 929, invocation 1134, and citation 297. And by comparing those numbers of the size, it's not hard to find that the classes are imbalanced, which means we have to adjust the class composition before we train something. Take the example of the description dataset. If we are trying to train the description classifier, we have to first create a new dataset based on all the description data and use some from citation, some from invocation, some from installation, and also a quarter from tree bank, which is adding corpus from the pandas. And by doing so, we have a new dataset combined with all the dataset I mentioned before. Using that new dataset, we will have a balanced one, which 50% are descriptions and other 50% are not. Using that one, we can train our new model, see if the performance getting better and better. After we actually build a training dataset we are going to use, then is to handle the feature. How to process the feature to make it able to fit in the model. Because most of the model cannot directly handle the input like text, like human languages. So we actually choose to vectorize them. By doing so, we first strip leading and ending spaces because they are useless, and we actually transform all the word into lowercase to control them better. And then we get rid of punctuations and stop words because they repeat too much times. So after that, we will have a bag of words. A bag of words means the rest of the words in the long article, in the long repository or README file will be collected as a bag, and we will count the number of the word existence in that bag to have our vector. And after we're doing all these jobs, we have the vector has over 2,000 dimensions, and the total number of training samples are 529, and we also keep 177 as the test will not be fed into the model until we test them. And last is talk about the model. What kind of model we are using? We actually use a deep learning model, which is a feed-forward neural network. We set it as a 6-layer network, and for the first layer, we actually transform from 256 dimension into 1,024, then 2,046, then blah, 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 going back to the 256. And during this process, we use ReLU as the activation function to get some linear transformation. The dropout rate has been set for on the first, second, and third layers because we try to avoid overfitting. So we actually have to set some dropouts on the first several generations. And at the very last, we do have another sigmoid activation function for the output layer. Why are we doing so? Because we want to make our output land between 0 and 1 so that we can have a better control of it. We can use this data to provide some like visualizations or provide some analyze and doing some future steps. And last, how to collect the result? How should we stop the training? Because we are training deep learning neural networks, and it typically will have epochs, so that we have to decide when to stop, how to choose between them. We actually choose F major, which has the following formula F1 as the loss function for our network. So among the first 30 epochs, which one has the highest F major will be collected as our final model. All right, the next step is to train the classifier for functions, which represent to the following picture in the workflow. The classifier for functions, the first thing to do is to simplify the question. Why we are doing so? Because the first thing is it is super hard to work on all software and all functions because there are tons of software, tons of functions on the internet. Of course, we cannot handle all of them. And it takes too much calculation, takes too long time. We don't have that, so we actually choose to simplify it. Another thing to concern is the concept of a software's function is very abstract. How could you define the function of a software by using the usage of it, the main written language, or the main-faced developers, or something? It's hard to say what kind of aspect represent function best. So we have to identify those details by ourselves to make this problem simpler to solve. And how to do so? The first step is to focus on data science software because all of our team members are data scientists. We are familiar with these software so that we can get a better handle of them. We actually know what does this software do so that we can manually label them by doing so. And as I mentioned, manually label them. We actually preset 3 different labels based on the main usage of one software. DA means data analysis, DM means data management, and deep learning means deep learning, and DL means deep learning. Sorry. Then the thing to do is to actually label them. Here label means one data, one input, one record can only has one class. Like if we are collecting something from PyTorch, and we can only label it as deep learning. Even though somebody will use PyTorch to do data management or data analysis, we will just record the main usage of this software. Okay, after the simplify of this problem, we get to know how to do this one, and we have to start to gather data. Basically, we just use the same data set as I mentioned before, which has been explained during the process of training the description data set, a description classifier. By doing so, we just search on GitHub and download more README files and split them into sentences, add them into the description.csv to expand the size of the CSV so that we have more of them. And after doing that, we will manually label all the data by DA, DM, and DL so that we have the Y label for our training. Because the input are still text sentences and SVM support vector machine cannot handle such an input, we have to use the same vectorizer function that we have used in the binary classifier for descriptions. Why we have to use the exactly same vectorized function? Because later on, we will combine the classifier for descriptions and the classifier for functions together. And if we use 2 different vectorized functions, they will have different dimensions. So try to avoid that. We have to use the exactly same one and use that one to transform our text as vectors, then fit into the support vector machine.
Okay, then it's the results for classifier for functions. To evaluate the model and to select the best kernel, the best value of parameters, we have to using some for loops to set the training and made our choice between all the training records. For example, here we have over 2,000 dimension of the input, which is a very high dimensional input data. So basically, linear kernel can work good on high dimensional inputs. So we have to train linear kernel SVM. Also, it is a multi-class classifier so that Gaussian kernel basically works good on most of the multi-class problems so that we have to train Gaussian kernel as well. By doing so, we set an automatically choose function in our code so that we can choose between the best formed one from the linear kernel and Gaussian kernel. To choose the optimal or the best value of parameters, we actually set another for loop which has over 80 combinations of the C and gamma so that we try all these values and select the one has the best performance of the J-code similarity. Okay, as I mentioned J-code similarity, how to measure the result, how to evaluate which one is better. Because this is a multi-class test, so we actually use confusion matrix, precision, recall, and J-code similarity as the measurement. And basically, we made all our choice, made all the judgment by comparing the J-code similarity.
Okay, after all the training and saving of our models, then we have to evaluate them to make sure they actually goes better than those in SOMEF. because this is the goal and the objective we set at the beginning of this project, that we have to compare the performance. From the following tables, we can see the upper one represent the best performance for SOMEF, and the lower one actually represent the best performance record for our project tool finder. And all the red numbers means our project performs better on this one than the SOMEF. Take an example of the citation precision 0.96. 0.96 is larger than the 0.89, and that means our citation classifier for tool finder has a better precision than the citation classifier in SOMEF. But you can see that the record, we only have 0.95 and they have 0.98. So it's kind of a trade-off between the precision and recall. But there is one except is the description one. The description one, our model tool finder has better performance on all these four statistics than the SOMEF. So based on those stats, we kind of had the better result than SOMEF, and we fit our goals that we set in the beginning of this project. Our model actually improved the performance on many aspects. Then let's evaluate the classifier for functions. The following picture shows the 20 times iteration for the supported vector machine, and it compares the J-code similarity. And as I said before, the threshold we set for this project is 60%, and for 3-class random guess, it will be 33%. The blue line shows our accuracy, which will be over 70% generally. And this result actually shows over 70% of the test case has passed, has been correctly classified. So I believe the classifier functions is a kind of huge success. Okay, last is the usage. How to use our project, how to see the interactive interface. To do that, at very first, you have to make sure you actually installed our project. You can follow the guide on our GitHub. Let's say by click here, you can see our GitHub homepage, and you can see the README file, follow the instructions here, installation. You can choose to use virtual machine, use your local environment, or use Docker, and these 3 different methods you can use to reach the goal. After your installation, you can go to the visualization folder and start the Docker server to see the result. I have already started for you right now, so you can directly see the result for now.
Okay, here is the page we designed for visualization for the classifier for functions. Why we intend to have such a visualization shows the probability of each class. Because our target users are software developers and scientific workers. These kind of people, they believe in statistics, they believe in math. So to convince them, it's better to show them something that actually shows the process of the prediction we made. That is more convincing to such a piece of customer segment. Then let's try some new inputs. Here is the repository that held by our instructor Daniel. Let's just simply click something, maybe this one, auto TS. I don't know what it does, but just copy paste it here and click the predict button and wait for several seconds. It shows the result. It says it has a 54% chance to be deep learning and another 45% to be data management. So it's kind of a project that can do data management using deep learning techniques. Probably I can see that.
Then next is the usage for binary classifiers for metadata. There are 2 ways to do so. Let's go back to the GitHub page. The first thing you can do here is to click here, click the binder badge, and it will build an environment for you using Docker on the cloud, and you can then see the Jupyter notebook and click here to rerun all the code. And after several seconds, a text box will show here, and you copy paste URL to here and see the result with step per second. Another way to do so is to install it into your local environment by install our project and the cd into binary classifier photo and run this Jupyter notebooks. It will do the same thing.
And the result is ready. And basically, we have the sentence first as the long string, then is the arrow to some tuple that represents the metadata it belongs to. To take an example of this sentence, AutoTS extends the Wings workflow system with new capabilities to customize general methods to specify datasets based on key characteristics of the data. And we believe that is a description. So this is how you read the result, how you use our binary classifiers for metadata.
Okay, that's our project, and we do have the following conclusions. First, for the existing four binary classifiers. As I mentioned before in the evaluation matrix, the four binary classifiers for metadata, we actually improve the position for most of them without losing much recall. And F measures are generally better than the existing ones in SOMEF, so it's kind of a success. For the classifier for functions, also mentioned in the evaluation matrix, the random guess rate for 3-class classifier will be 33%, but we have over 70 accuracy. It also finished our set goals as 60%, so it's kind of huge success on the classifier for functions. And last, for the visualization result, we do have two separate way to use our project. First one is the function prediction using Bogus server, and another one is the binary class classification using Jupyter Notebook, or using Binder to build a Jupyter Notebook on the cloud. And for the future steps, we do have the following concerns that we are thinking about doing and can be finished in the future. The first thing is to combine the four separated binary classifier, because for now, if I have a sentence A, and we have to first run the description classifier, then installation, then invocation, and then citation. And then it will tell you, oh, if it belongs to description, invocation, citation, or installation. I want to create a new one which will be a multi-class classifier that if you give this classifier a sentence A, it will tell you how much chance it can be description, how much chance it can be an invocation, things like that. And the second thing to do is to speed up the process of our calculation. Now the predict takes like 10 to 20 seconds to finish for one input because the vectorize takes a long time. I want to find some new vectorize method to speed up this process. The last thing to do is combine the Jupyter Notebook with the Bogus server. For now, our user has to use it separately for the function classifier and the binary classifier, and they have to jumping from here to there. I want to save their time on doing such things, so the next step of our work will be combine these two interfaces together. Okay, that's it. Any questions?